Okie dokie. So thanks very much for joining us today. My name is Joseph Guyan. I'm a product manager at ANSA Data Analytics. Very quickly, if you don't know who we are, we analyze case hall logging data. We've been doing it for about 20 years now. We're an independent specialist in the field, working for service companies and operators all around the world. Multi-finger caliper processing, it's been a big part of our day-to-day work for that whole period of time. So it's fair to say that we understand this topic inside out. We're going to be walking you through quality checking of multi-finger caliper data ahead of interpreting. And doing all the heavy lifting today is my colleague Jenny Mickey. She's a data analyst at ANSA. She regularly works with challenging multi-finger caliper datasets, and she'll be using real examples along with training datasets to show what good data looks like and also what can go wrong. Jenny, can you quickly say hello and give a few words?
Yeah. Hi, everyone. Thanks for popping along today. As Joe's mentioned, Caliper data is definitely the service that I've had the most experience with over the years. We've seen some weird and wonderful features in data sets, which keeps it all exciting, I suppose. But yeah, I'm looking forward to sharing some hints and tips with you all today.
Great stuff. So we've also got a poll that's going to go live now, please. You can answer that in your own time, maybe in the first introductory slides before Jenny really gets started. That'll maybe inform some questions at the end as well there. So if that poll's alive, there we go. So on the topic, it is a big topic. There's a lot of possible scenarios. What we're going to do is we're going to do our best to cover as much ground as we can. Honestly, with each of these subtopics, they could take an hour on their own, to fully digest. So we might be a bit guilty of throwing out a few unfamiliar terms with this high-level explanation. But what you will get today is a solid foundation that will let you start QCing your own data and also ask questions of people like us if you're receiving the reports. You can ask those questions at a higher level. Just before we start, we do have a lot of material. So we're not going to take questions as we go, although I'll keep an eye on the chat. So the panel, that chat is live just now. I'll try and answer some of those as we go. But we're also setting aside 15 minutes at the end for a live Q&A. So if you could have the next slide, please. So very briefly, why inspect your wells? What is a multi-finger caliper? First up, operating your well safely depends heavily on the condition of your tubing and casing. And what we're looking for is the metal loss from corrosion and erosion and other damage, but also deformation and deposition. To assess your tubing and casing, the multi-finger caliper is a tried and trusted tool. It takes direct radius measurements that describe the inner profile of the pipe, allowing you to spot any damage that could disrupt production. It's also frequently run ahead of other intervention work, for example, to assist in plug set operations or to inform scale treatment plans. It's a mainstay of well integrity logging, and it's been run worldwide for decades with high confidence in the measurement. But that doesn't mean you can skip checking the output. Let's go for the next slide. Why does data quality itself matter? So it matters whether you're holding the report or whether you're generating it. For operators, the decisions you make rely on confidence in the data. You're ultimately paying for answers to specific questions, and good QC is what underpins those answers. If the quality is poor, even straightforward optimization or intervention decisions become slower and much less certain. And for service companies, QC is how you deliver on what you've promised. It helps you catch issues early, present results you can stand behind, and avoid the rework that nobody wants. As for analysts, the QC is the diagnostic stage. It tells you what the data can genuinely support before processing and interpretation begin. So you can see why everyone wants a solid QC stage. It protects the value that operators expect and the credibility that service companies need. Next slide. So with that all in mind, here's a rough overview of how we'll be spending the next part of the session. If you can pretend that you're sat at your computers, you've just received your data from the field, Jenny will be starting with an overview of the QC checks and of the required field information, showing you how to identify trustworthy versus problematic data using a mix of real cases and training data sets. And you'll see the exact impact these data issues have, even if they're missed. We'll also be using Clarity. That's our own software for multi-finger caliper processing. And we've got recordings on YouTube that go into full detail about Clarity. But for now, the main thing to know is that we've developed this software to use artificial intelligence and machine learning to help experts and beginners alike get better, quicker results when compared to legacy software. If you want to know more about it, just drop a note in the chat or reach out to me on LinkedIn. So remember, throughout the session, please use the chat. I'll try and get to the questions there. And at the end, we do have that 15 minutes where we'll answer some questions again. With that, I'll hand over to Jenny.
Cool. Okay, thank you, Joe. So now that Joe's given us a brief summary on the tool and its uses, we'll get into the general data expectations and the requirements. Okay, so prior to Caliper log, we look to receive the following information. So for QC purposes, we need the schematic to be able to check that we've received the correct data. We've had that before. And also to confirm that the reference points and the tubing dimensions prior to login. We need the deviation data to check against the deviation from the tool and to ensure the sensor is working correctly. And also, it's good to know the survey objectives, because sometimes even data sets with data issues pass the QC stage if the survey objectives can still be met. Once we receive the data once the data has been received from the well site, we require the engineers to apply the following to the data before creating their output file. So temperature compensation. So this is to correct for any drifts introduced as the fingers heat up. And this I'll go to in a wee bit more detail later on, and I've got an example of that. Tool calibration. So this is usually the pre-survey calibration acquired for each individual finger on the caliper. We also require non-centralized data. So most of the acquisition softwares can centralize the data. However, we require the uncentralized data so we can obtain a full QC. And I'll explain how many features could be missed or misinterpreted if only the centralized data is looked at. And lastly, it's good to know if there's any depth corrections that have been applied. We prefer non-depth corrected data, but we just need to know either way. Okay, so now I'll move on to explaining the LQC checklist for both the raw and the centralized data. Okay, for this presentation, as Joe said, I'm using Clarity for the examples, which is our in-house software. Excuse me. However, the QC steps will be similar using softwares from elsewhere. So the first thing we need to do is import and check the raw data. And we need to ensure that we have, I'll just get my wee pointer. We need to make sure that we have all the data that we're expecting in the file. So for example, if there is a temperature or a pressure sensor on our tool string, and the data from this may add in our analysis. So it's good to have them from the start so we're able to depth correct them together so any anomalies are kept at the same depth. And we also need to make sure that we have all the finger data present. And it's good just to look at the tool string diagram that we receive to make sure that we have everything that we're expecting. Another thing we need to check is the length of the file that we've received. So if we know that they have logged from 4,000 feet to 2,000 feet, we're expecting 2,000 feet of data. If we don't have that, we can then ask the engineer at that stage to make sure that we're not going to miss anything. Another one is the sample rate. If the data has been logged or exported at an incorrect sample rate, we could miss features in the well. So higher the sample rate, the better. More data, the better. And we also need to make sure that we have the correct tool bearing sensor is selected and the direction is correct for the tool that we have. So we can also check this in the raw data window, which will be explained in more detail next. Okay. So I'm just going to move this away 2 seconds. I'll just take a wee moment here to explain what it is that we're looking at for those that maybe aren't as familiar. The VDL tracks are plotted vertically for the individual arms. So here we've got arm 1, arm 2, all the way up to arm 40 for this 40-arm caliper. The VDL color map is set by the user and may vary between clients. However, we mainly use color maps that correspond to the nominal values of the pipe that are present. So in simple terms, this then shows us the areas of lower ID in the blue and areas of higher IDs in the green, yellow, or like the red here. And this all depends on the offset of the tool when we're looking at the raw data and the severity of the features when we're looking at centralized data. So if the color corresponding to a feature doesn't look quite right on what you're maybe expecting, it's best to check the color map has been set up correctly. Okay, so what I've said before, one of our checks is to check the tool rotation. So the rotation sensor is important because it tells us the orientation of a specific arm within the cross-section of the well. And by knowing the orientation of the arm, we can determine the direction of any feature detected in the well. We can verify that the rotation sensor is working by looking at the raw data. So although this tool string is centralized within the well, using centralizers, gravity still can have an effect, causing the tool string to rest slightly towards the low side of the well. And this offset is called eccentricity. And a certain amount of eccentricity we are expecting, and it is something that we can rectify during processing. So if we're looking at, so with the tool sitting towards the low side, the result is the arms positioned on the high side of the well record higher IR values, shown in red, and then the arms on the low side are shown in blue and have lower IR values. So using the rotation measurements from the tool, we can calculate which arm should be on the high side at every depth. And I've highlighted those expected to be on the high side in this gray sort of curve here and here. And as you can see, these arms here consistently correspond with the higher IR readings, confirming that the rotation sensor is performing as we'd expect. So the rotation sensor is also essential for correctly orientating features within a well. So for example, once orientated using the rotation measurements, this feature that we can see in the centralized data is shifted to the center of the image. Got some things on my screen here. On the center of the image here, so it's clearly shown that this damage is on the low side of the casing, with any features on the high side shown at the edges of the VDL there. So knowing the orientation of the damage could also help us identify its likely cause. So for example, metal loss on the low side may indicate mechanical wear or debris-related damage, whereas corrosion caused by corrosive gases is often found towards the top of the well. So it's useful data to have and observations to make. Okay, so I've just used the rotation explanation to set the scene a little and look briefly at raw data. So now we're going to have a look at a training data set where I have introduced a few different features we would be looking out for during the QC process. It's difficult to find the perfect training job that shows us a mix of different features. So I've kind of introduced some features so they maybe don't look as authentic as they would if you found them down hole, but it'll give us a good picture of what to look for. And for the issues present in our data set, we'll learn how to identify them. And then for anything that we don't see, we'll show some examples of once we nip back into the presentation. Okay, let's see if this works. Joe, you can maybe let me know you see my clarity screen there yet? Or do we nod? Yes, cool.
Good.
Okay, so what I have done here is I've imported the data and full range of the image. So we're seeing the full data set, which runs from 1340 up to 0 feet. So arm 2 is the first one that it draws my eye. In this arm, because it's blue all the way throughout, it's obviously reading lower than all the other arms throughout. So the first thing I would do is look at the cross section and get these values up. And yes, we can see that it's reading much lower than all the other arms. And if we look at the actual value, it's a negative value, which is impossible to record with the Caliper tool. So this must be a tool error, and it's something that we can arrange during processing. So that would be my first note before I move on to process the data fully. The next thing I would look at, if I get rid of the cross section there, would be the maximum, mean, and the minimum curves. The minimum curves obviously have been affected by this low reading arm. I don't have time to really look through the schematic with you all today, but here we can see a completion item, which we can line up with the schematic. Here's another item, and down here is maybe like an SPM or something down here. However, we cannot correlate any of these higher IDs with anything in the schematic. So let's have a look at these features. So in first look, I can see these little higher ID features here, 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 and here. And the first red flag for me is the fact that they're all observed on the same arm. Sometimes if we have an issue with one arm, even if the tool is rotating, they're still seeing the same features, which may indicate that this arm has some sort of error. If we look into these individual features in more detail, we can see that it's only been recorded over one data point, which is 0.01 feet or 0.12 inches in this example. However, the maximum value we can see up here is 10 inches. So this is impossible. So if you look at the way that the caliper fingers are made, they have like a tip. Now for that tip to be able to go through the whole pipe thickness and stretch even further into the wellbore to get to 10 inches is impossible. Mechanically, it's impossible. So these would be definitely flagged as spikes that need to be removed during processing. So I would investigate this arm all the way through and remove them. We've also got these wider looking features here, but again, they're not very long in length, maybe a couple data points, and they're still reading over like up to 10 inches. Still not, the caliper is not capable of reaching that far into the wellbore. So these ones would also be getting removed. As we go down the data set, we can see that this is a completion item here, looks okay. We can see this feature. Now this feature is longer in length. It's about 2 feet in length and is got a maximum reach of 6 inches. So this could be possible for a wider feature in a feature that's longer in length. The caliper arm could reach that far into the wellbore. So we'd leave that and have a look at it in centralized, once it's been centralized, just to make sure. We can kind of see a general like increase track here. So that's something to look for once we centralize the data. We can see these minimum lower reading arms, maybe not quite the same as the neighboring arms beside them. This could be something like a clogged arm or things, or it could just be an arm that just maybe needs tweaked in the recalibration. So we'll have a look at them again once it's centralized. Down in this lower section, we can see that the tool is sitting closer to this side, and then it moves to this side, and then it's back to this side. So this is called movements in the tool trajectory as it moves through this part of the well. Now, this could be due to deformation, or it could be just the way the tool's moving past this item. So again, we can make a note of this so we can look into it in more detail. And down here, we see some low readings here and here. If we look at the cross section, we can see that these arms have likely been affected by deposition here and here. This is your arm that's not reading correctly. So we'd be looking at to see what they look like once they've been centralized. Okay, so as if by magic, I've centralized the data, and we can see that this low reading arm is still present and still needs removed. That's fine. We have these data spikes have become more prominent in the data, along with these ones that are all reading 10 inches. So we can remove them. These lower reading blue arms are still present. So to decide whether these are clogged and not representative, or whether they just need a little tweak in the recalibration, I would look in at an item or a connection. So here's a connection between two tubing joints, and we can see that the profile is similar to all the other arms throughout here. So I would say that they are still reacting to features, but they may just need a recalibration to bring it back into line with everything else. So that's something we can do in processing. This metal loss looking track is still present. So again, I would note this down for the reporting stage. Down at the bottom here, we can see quite a severe looking image. So if we look at the cross section, I'll put the grid on. Let me zoom out a wee bit. Zoom in a wee bit. We can see that in this section here where we have no features, we can see that this is centralized really well and lines up very well with the grid that we have here. When we move into this data, into this feature here, we can see that these arms are being affected by the deposition, However, these arms are still very well centered around the circular grid, with the center of the tool in the middle. However, when we move further into this feature, we can see that it shifts slightly. I don't know if you can see that slight shift to the right as we move up into this feature. So these arms here have come closer to the grid, and these ones are moving further away. So we can see that the offset of the center of the tool isn't quite right. And this causes high IDs here and here, and lower IDs here and here. So we can see that in the higher IDs in this green. So these are not true features of the well. I wouldn't call this metal loss. However, we need to look at further into the processing to make sure that this is removed so it doesn't get misinterpreted. And this section as well, we can see it's definitely off center. We've got higher IDs here and here, which are not true. These arms all around here, I think, are touching the tubing surface, but when compared to the grid lines, it's very off. So again, we'd need looked at in more detail for the during centralization. Okay, so a quick thing to look at for when you're in Clarity that we have here is the QC module. So this just gives a first quick run through of the data and might point out some areas that you've maybe missed or maybe not thought to look at. So in this one, it looks like for stick and slip, and it's passed. I agree. I don't think we've seen any severe stick and slip moments in this well. Clog sensors. So this runs from the top depth to the bottom depth. So that's referenced in this arm 2, which is reading lower throughout. And we've also got data spikes. So it's identified all the data spikes and it's listed the depths. So this is really handy for if you need to go through and edit these all individually, or you want to make sure that you've actually noted them all down correctly. And yeah, and we've also got the telemetry dropout and null values of both passed. So this is a good way of just making sure that you've looked at the data fully and have identified everything that you need to. Okay, if I nip back into the presentation. Okay. Okay, so these were all the things to look out for in the data set, and I think we've identified all of them, if not most of them. So the QC process for me is for note-taking. It's to list areas of concern with the tool and areas that we need attention during processing, and also to note down any features that need reported on. There are many other features and issues we need to look out for in a data set, especially those which may be misinterpreted. So we'll have a look at some of them. Okay, for this first one, it's stick and slip. So a quick description. So as the winch pulls the tool string up the well, cable friction and debris buildup can cause the tool to temporarily stop moving, which we call tool stick, before suddenly releasing and jumping upwards, which we call tool slip. So it's important to recognize when stick and slip has degraded the data to the point where it's no longer suitable for processing, or whether the data quality remains acceptable for the survey objectives, but may just need to be treated with lower confidence. So this example shows a pronounced, let me get my little pointer again. So this example shows pronounced stick and slip event, and the stick intervals are clearly visible where the tool becomes stationary, and repeated measurements are recorded over multiple depth intervals. This is just due to it being recorded in time and then put into like a depth file. So these are followed by areas of slip, where the tool suddenly jumps up the well, which potentially causing the tool to dance across important features. So stick and slip, it's not always a significant issue, but it is something that should always be assessed. So in the left image, we can see approximately 8 interval instances of stick and slip, which have occurred over a 20-foot interval. The data becomes stretched over approximately 14 feet of this section, meaning a significant portion of the interval of the internal surface is not been imaged. And then in here, we've only got 7 smaller stick and slip events over a shorter 5-foot interval. So the stick intervals are much shorter, so the impact on the data quality is minimal and it does not compromise the survey objectives. So being able to identify stick and slip is also important when measuring the length of components or features within a well, as these events can lead to inaccurate length estimates if they've not been recognised. Okay, eccentricity. This is one of the most important ones, I would say. So eccentricity is one of the most important logging parameters to assess during data quality control. So if it's not identified at the QC stage, it could lead to misinterpretation of many well features. And this is true for many other tools, such as like the radial bond tool for cement evaluation and many other logging measurements. So understanding whether the tool is eccentered and by how much provides the valuable insight into the efficiency of the login and also the well conditions. And it can help identify whether we've got a failed or ineffective centralizer, whether all the caliper fingers remain in contact with the internal wall, in areas where well deformation is forcing the tool string away from the center of the well. So assessing the eccentricity ensures that the login measurements are representative of the well geometry and provides confidence in the interpretation of the survey data. So I've got a couple examples on eccentricity here. So this first example shows us how high well deviation and poor centralizer strength can cause some caliper fingers to lose contact with the tubing wall. So this is a standard 40-arm caliper and has a maximum range of 7 inches. So any recorded values greater than 7 inches, which we have here, indicate that those caliper arms are likely no longer in contact with the tubing wall, or instead they're measuring open space. So in this example, 36 of the caliper arms remain in contact, while 4 adjacent arms along the high side have lost contact. So the effect is harder to see in the raw data, but if we centralize it, and I've zoomed into the bottom of the data set here, these invalid measurements from the 4 arms can distort the reconstructed internal profile, creating misleading low ID features or provides a false overall cross-section. So understanding this behavior is essential when interpreting caliper data, and as apparent defects may be the result of tool eccentricity rather than changes in the tubing surface. So for this example, these lower IDs may be misinterpreted as deformation or an area of deposition, which is not true. Okay, for the second eccentricity example here, we can see that we've got relatively consistent maximum and minimum values alongside an increase in deviation around about the same depth. So this prompts a closer examination of the eccentricity, and the amount of eccentricity that can be considered acceptable all depends on the pipe size and the survey objectives. So however, in this case, the tool is displaced by more than 1 inch from the center, which can be seen in this MOE curve, which is the magnitude of eccentricity, which runs from 0 to 1.4. So round about here, we're over 1 inch away from the center, which is quite high considering caliper data. So this shows a clear indication that the data may be affected. So once we centralize it, we can investigate further. But at first glance, you may look at this and the image appears to show 2 tracks of metal loss. We have this one here shown in like the lighter yellow, orangey, reddy colors, and this one here, similar here. So, however, the higher levels of tool eccentricity and the orientation of these features, it becomes clear that the certainty of these features should be questioned. So rather than indicating true metal loss, these apparent defects are likely artifacts introduced by centralizing the data acquired with an ecenter tool. So we really have to look out for this. So looking at temperature compensation, so the sensors within the caliper have a tendency to drift as they heat up, causing the raw caliper data readings to become increasingly inaccurate as the tool is exposed to temperatures above standard conditions. So this introduces a gradual temperature-related drift in the caliper measurements. So obtain measurement accuracy, temperature composition is applied using the acquisition software after the survey has been recorded in the field. So depending on the well temperature, it could be very obvious when a temperature compensation has not been applied. In this example, the caliper readings begin at lower values and they gradually increase towards the surface. And despite there being no corresponding changes in well geometry, so there's no indication of metal loss and there's no indication of increased deposition. So recognizing this trend during the QC is important as it allows us to distinguish between genuine gradual change in the well and a temperature-induced measurement error that must be corrected during the processing and to be able to provide accurate measurements. Okay, right, this is like the last sort of section I have to speak about today. So here's some basic reasons for deformation, and they're presented here. But I'm not going to go into these. However, I will show you some examples of what it can look like in Caliper data. So in this example, the separation between the maximum and the minimum IDs are present at the same depths as we can see in the raw data. So these would be described as isolated sites of ovalization, which affect the circular profile of the tubing and are easily identified both in the raw data and the centralized data here. However, in this example, we can see that buckling is present, indicated by the presence of changes in tool trajectory and increased variable separation between the maximum and minimum IDs. So the areas where the maximum and minimum IDs become closer to the mean, this is where the tool is more centered in the well before moving and becoming more eccentered as the maximums separate. So it comes closer to the middle and further out, closer to the middle, further out. So this buckling of the pipe is forcing the caliper to move like this throughout the tubing. So what do you think we would expect the internal profile to look like here? So once I centralize the data, it's clear that the circular profile of the pipe has not been altered. However, this type of buckling can still cause intervention issues, depending on like the length and the size of your tool string. So this shows the importance of QC in the raw data, as this would not have been identified if we'd only received centralized data. Okay, so this is a summary of the key log quality control checks to perform on both the raw and centralized data before interpretation. So carefully reviewing the data before processing and interpretation ensures that the apparent features are genuine and are not artifacts introduced by the tool, the acquisition conditions, or the data processing. So performing these checks gives confidence in the final results and helps prevent reporting defects or features that don't actually exist. Breathe.
Yeah.
That's me.
Well done.
Sorry, there's a lot of talking.
Yeah. Like we said at the beginning, there is a lot to go through, and
There's
a
a
lot of
lot.
those topics are quite big.
Yeah.
And ideally, you'd probably want an hour to spend on one of those two,
Oh, at
some of
least,
those
yeah.
topics. Yeah.
Yeah.
Thank you very much for taking us through all of that.
No problem.
Just to briefly recap, we started with the broader reasons why data quality matters. Talking about how good QC starts with properly understanding the context. That's really important. The well details, the logging conditions, and why you're logging. Are you going to achieve those objectives? And then we started to look into detail about the different aspects of the data that need to be checked, how you actually carry those checks out, and how those results affect the way you process and interpret. And then, like I mentioned, how can you actually achieve the objectives of the logging job? And that brings us to the end of the slideshow. Thank you very much for all joining us.